Welcome to join today's class. In this class, we'll explore the convolutional neural networks, which is one of the most important type of neural networks in deep learning. Today, we will first mention the basic operations inside the networks, and then review the new types of convolutional neural networks in the next few years. Convolutional neural networks is also known as CNN or ConvNet. It was invented for image classification. Here is a picture that visualizes the operations of convolutional neural networks. This picture is extracted from this blog, a beginner's guide to understanding convolutional neural networks. Regarding an input image, we first apply convolution filters to this image, to all the pixels. The convolution filter is used to extract features. Features are the representative parts of an image. For example, the beak and the feathers are the features of a bird. Once the features are extracted, we downsize the images using max pooling or other methods. The reason to downsize the image is to apply filter to larger area of an image. The features at later stage are usually more semantic and can be interpreted by human, such as the head of the bird or eyes of the bird. Finally, we need to flatten the vectors into one-dimensional vector. If we are doing image classification, then we can apply the softmax for multiple class. The output layer's dimension is equal to the number of class in our dataset. Before talking more details about convolutional neural networks, let's review what digital image is. The digital camera converts an image as pixels. The pixels are saved as array in a computer. The size of the array is the height times the width of the image times 3. This is because a pixel is represented by 3 colors: red, green, and blue. We usually use 1 byte to represent the brightness of a pixel color. The range of 1 byte is from 0 to 255. For grayscale image, we will have only 1 byte. For colorful image, we have 3 bytes for 1 pixel. Suppose this is the image we see, and it will be converted as the array of numbers in computer. So this is what computers see. Remember, it is a 2D array for grayscale image, but 3D array for colorful image. There are 4 major tasks in computer vision: classification, localization, detection, and segmentation. Image classification is the most common task, which is to classify an input image into one of the predefined classes. However, image classification assumes that there is one object in an image, and the object is better in the middle of the image. Therefore, we cannot apply image classification to photos with multiple objects. The second task is localization, which goes one step further than classification by finding the bounding box. So now we know the location of the object, but it's only handled one object in an image. For real applications, we usually want to find all the objects in a photo. This task is called detection. Object detection can find all the objects in an image, and the objects do not need to be the same class. Object detection is the very fundamental task of computer vision. The final task is segmentation, which is not only localize the object, but also segment all the pixels of the object. Segmentation can find the precise contour of the object. This feature is important for some applications such as autonomous driving. To better understand convolutional neural networks, we need to know the convolutional theorem. The convolutional theorem states that Fourier transform of a convolution of two signals is the pointwise product of their Fourier transforms. In other words, the convolution of two signals, suppose f and h, in one domain, spatial domain for images, or time domain for time series signal. The convolution of two signals in one domain after Fourier transform will become the pointwise product. It will become the product of their Fourier transforms in another domain, usually frequency domain, and vice versa. The convolution of signals in frequency domain after Fourier transform will be the product of the signal in spatial domain. Convolution can be viewed as applied a function h to input signal f and generate new signal g. It has wide applications in signal processing, engineer, image processing, to name a few. Let's see some examples from Wikipedia. Suppose we have two signals, f and g. To calculate the convolution, we first reverse the signal g, and then calculate the product of g and f, and then we shift g. So the new signal is the integral of the product of f and the reverse g. Okay. As we can see, the shape of the input signal f is changed by the shape of signal g. So signal g is work as a filter of signal f. By applying the triangle signal to the square signal f, we can get a fin-like new signal after convolution. Note that convolution is commutative. We can change the order of g and f and get the same results. The other relevant operation is cross correlation. The difference between correlation and convolution is that correlation does not reverse the signal of g. Correlation will generate different shape of output. But more importantly, that cross correlation is not commutative. So the order of f and g will lead to different results. Another operation is autocorrelation, which applies the signal to itself. Shift the signal and calculate the integral of the products. In this case, the square signal of f becomes a large triangle signal. Convolution is used in image processing to extract features. The most famous operation is Sobel filter, which can be used to extract the edges of an image. There are two 3x3 kernels in the filter. One is GX, which is used to extract the vertical line, to extract the vertical edges. Another one is GY, which is used to extract the horizontal edges. From the filter values, we can see that the Sobel filter wants to calculate the difference of the two sides of the middle, right? Or you want to calculate the pixel value difference. This is because an edge is a line that have large pixel value difference of its two sides. The Sobel filter wants to detect the edges by calculating the difference between the two sides and ignore the pixel value in the middle. Once we have the kernel matrix, we will apply the kernel matrix to the whole image by moving the kernel matrix pixel by pixel. Here's an example. We move the kernel matrix in the zigzag direction. Okay. And we calculate the response. The new output will be the response of the kernel at different locations of the input matrix. At the boundary, we can padding zeros to the boundary of the image. This way can keep the output have the same dimension as the input matrix. It's called zero padding. The moving distance is called a stride. In this case, we set the stride to 1 in this example. We can detect different features by changing the parameters of the filter. Here's a curve filter example. Suppose we have a large filter and we want to use it to detect a curve. We can set the curve, the weight of the curve's position as 30 and otherwise 0. So we will have a filter with a lot of zeros, and the only values of the filter is correspond to the curve shape. If we connect all the non-zero values, you can see the shape of the curve. The curve is shown in the picture on the right. Now suppose we want to apply the curve filter to an image of a mouse. We start at the bottom of the image and apply a curve filter. The pixels of the bottom of the mouse is shown here. Let's apply the curve filter and calculate the response. Let's apply the pixel-wise multiplication. So ignore the zeros. The first value is 50 times 30. The second value, the second non-zero value will be again 50 multiplied by 30. Okay, and then the third is the same. The fourth will be 20 times 30. Okay, so eventually we will get a very large number, 6,600. This is the output response of the curve filter at the bottom of the mouse. We continue scaling and move the filter to the head of the mouse. You can visualize the head of the mouse by connecting the non-zero values. So what happens if we apply the curve filter to the head of the mouse? You can see that the non-zero value of the filter is applied to the 0 pixels of the head of the mouse. So the multiplication and the summation is equal to 0. So our filter has no response at the head of the mouse. There is no curved shape at the head of the mouse. From this example, we learn that if the target shape is detected, we will get a large output response. Otherwise, we will get a very small or either zero response of the filter. We have learned how convolution filter works. Let's back to the convolutional neural networks. In fact, a convolutional neural network consists of a huge number of convolutional filters. Each filter can extract different kind of feature. Most important of all, the filters are not designed by us. The parameters of the filters are automatically learned by the optimization algorithm. In other words, convolutional neural networks will learn how to extract different kinds of features by itself. In modern convolutional neural networks, there are usually millions of convolution filters in a network. The huge number of filters can help the network to identify thousands of objects. We know that there are multiple layers in a network. The filters in the first few networks are focused on small edges or curves or lines, which are not meaningful for humans. After max pooling, the deeper layer will extract more semantic features. For example, suppose we apply the convolutional neural network to an image of Kate. The first layer may extract the edges or curves of the head, or the head of the nose, or the shape of the ear. After going through several layers, in the deeper layer, the filter can extract the eyes or nose or ears more semantic to humans. This is an oversimplified example, but it can help to explain what features the convolution filter learns in the neural network. Let's create our first ConvNet using Keras to classify MNIST digits. Again, we first import layers and models from Keras, and then create a sequential model. Okay. Once the model has been created, let's add a conv to the layer into the model. The first layer needs to assign the input shape, which is 28 by 28 by 1, because we are processing grayscale image of MNIST. And then we need to assign the size of the filter. We choose a 3 by 3 filter. Finally, we need to assign the output dimension, which is the output channel size. We assign it as 32. Then we need to go through a max pooling. We can define the max pooling size. Here we choose 2 by 2, which means the image will be downsized to 1/4 of the original image. And again, for the second convolution layer, we assign the 3 by 3 filter and 64 output dimension. So the output is corresponding to the channel size. And we can see a trend that the deeper the layer, the larger the output channel size. Okay, so in a typical convolution neural networks, the width and height, the dimension of the image, is shrinking. Is the size and the width and the height will be divided by 2 after every max pooling. However, the size of the output channel increase. In other words, the number of filters increase when you go deeper in the network. For each layer, we choose the rectified linear unit as our activation function. We can use the summary function of Keras model to print our model's information. The summary function can print the name of the layer and the type of the layer, the output shape, and the number of parameters of each layer. Let's see how to calculate the number of parameters. In the first layer, we choose a 3x3 filter. Right? So the size of one filter is 3 times 3 plus. After we apply the filter, we need to have an activation function. So we have one parameter for bias. So the number of weights is 3x3 times 1. And this is the parameters of one kernel, and we should multiply it by 32 because the output channel size is 32. So the total is 320. One thing to note is that the output shape is slightly smaller than the original input. The original emitted image is 28 by 28, but now the output is 26 by 26. This is because we didn't use zero padding, and when the 3x3 filter meet the boundary, it will lose some size of the image. Okay. Then after the image passes through the max pooling layer, both the height and width are divided by 2 because we choose the 2x2 max pooling layer. For the second convolution layer, the ID is convolution 2D2. The parameter is much larger than the first layer because now we have a larger input dimension. The size of the convolutional filter is 3 by 3 by 32 plus 1 bias, and now we need to multiply the filters by 64 because we have a 64 output dimension. So the parameters are much larger than the first convolution layer. You can calculate the number of weights of third layer by yourself. The outputs of a convolution layer is also called as feature map. Let's look at this line of code. Now we understand that this line means we have a convolution 2D layer that accepts the input shape, input image with size 28 by 28 by 1. It's a grayscale image. So we receive a 28 by 28 input grayscale image and computes the 32 filters over it. We will learn the 32 3x3 filters. Each filter has a size 3x3 and can extract different features. All the weights of the filters are automatically learned by the optimization algorithm. Suppose we have an input image 0 on the left, and after apply the single filter which can extract the diagonal features, the output response map, the feature map, also called response map, will be like this. Now we can see that we have large response, the brighter pixels on the diagonal part of the handwritten digits. So this is how we learn the filters and how the feature map may look like. There are two terminologies need to be clarified here: kernel and filter. In image processing, we only say filter. Filter can change the shape of the input signal. But in convolutional neural networks and image processing, we use the term kernel. We use kernel to refer to a 2D array of weights. And the filter means the 3D structure of multiple kernels stacked together. Remember, the color for images are actually 3D tensors. The third dimension contains RGB colors, red, green, and blue. And actually, the dimension of channels changes depends on each layer. The third dimension is called channels. Remember, we defined the number of channels in the beginning of the conv2D function. You will see a 1x1 filter later. The 1x1 filter is actually focused on processing the channels. After creating the convolutional part of our network, we need to flatten our network and add a classifier on top of the ConvNet. So we call the flatten function of the layers and then add dense layer. Usually we add one dense layer between the final output layer. Because we are doing multi-class image classification, so we add the softmax with 10 dimension. We are classifying 10 digits as final output layer. Usually we will add one dense layer between the flattened vector and the final output softmax layer. The summary of the final complete ConvNet is here. We have added 3 convolutional layers, 2 max pooling layers, and 2 dense layers in our network. There are around 100,000 parameters in our neural network. You may notice that the height and the width of our image become a little bit smaller after each convolution layer. This is because whenever our kernel hit the edge of the images, we will lose some pixels. For example, suppose we apply the 3x3 filter to this 5x5 feature map. We can apply three kernels, and the new output width will be 3 because we can only apply 3 kernels. The new output width and the height will be the input width and height minus the kernel size, right? Plus 1. To solve this issue, to keep the same width and height of the input feature map, we can use padding. Basically, we pad zeros around the images. If we pad zeros around the images, we can keep the same width and height of original input feature map. Another parameter that we can set is stride. Stride is the moving distance of the kernel. Usually we set it as 1, which means we move the kernel pixel by pixel. For an 7x7 input feature map, if we set stride with 1 without padding, the output will be 5x5. If we set the stride to 2, which means we move the kernel with 2 pixels each time, then the 7x7 input feature map will become a 3x3 output feature map. With stride 2, we can roughly divide the width and height by half. In convolutional neural networks, we need to downsample an image. The most common technique is max pooling. We can also use average pooling or stride to downsample an image. Right, we can set the stride to 2. However, max pooling has best performance for image classification and object detection. The idea of max pooling is simple. We just select the maxima value inside the filter. Suppose we have a 2x2 filter, and we apply the max pooling to a 4x4 image. Then in the first area, we select 6, which is the maxima value in the 4 pixel. And for the second area, we select 8. For third, we select 3. And for final one, we select 4. So after max pooling, we will have a 2x2 feature map. Okay. Max pooling is intuitive because remember that we are trying to find the most distinguished part as our feature in an image. And the most distinctive part will have largest response after the filter. So select the maxima value is reasonable. This is usually the best feature in this region. Now let's see another example from our textbook. We will train a model to classify cats and dogs. So it's a binary classification. The dataset are downloaded from Kaggle, which is a dogs versus cats competition. We select 2000 cat and 2000 dog images. Here are some examples from the dataset. We'll build a convolutional neural networks to classify the images. Now we create a CNN model using Keras. First, we import layers and models, and using the model's sequential function to create a sequential model. Then we start to add convolution 2D layers and the max pooling layers. Okay, the first layer need to assign the input shape. Now the input colorful image size is 150 by 150 by 3. Okay, and then the output feature map will go through the max pooling layer. Okay. We all use the 3x3 filters. And note that the feature map usually increase with deeper layers. Alright, so the original output channels are 32, then the second output channel are 64, and then 128 and 128. You are free to try different combinations of the parameters. Finally, we flatten the feature map and add one dense layer. The final output layer is a sigmoid function because we are doing the binary classification. In our previous example, amidst the digit classification, the images has been preprocessed, decoded as array of pixels. But in this example, we need to process the pictures by ourselves. So we need to write an image generator by ourselves. The image generator will first read the picture files from directory and then decode the image, usually saved in JPEG format. Decode the images into pixels, RGB pixels. And then we need to convert those into floating point tensors. Also, we need to do the normalization, which rescale the pixel values. The original pixel value is between 0 and 250, saved as 1 byte, to the 0-1 interval. Okay. So here's the code. First, we import the image data generator class from Keras preprocessing image library. Okay. Then we can use the image generator to preprocess or rescale our images. Okay, and we need two generators. One is for training data, and another one is for test data. Okay, so we can assign a folder to the data generator. The data generator will read images and decode images for us. So we will save the train and the validation images in different directory. Okay, the train data generator will read the images from the train directory, and we set the target price to 150 by 150. The bench size is 20 and the class mode is binary. We use the same parameters except that we assign different directory for test generator. Remember to separate the training data and the test data, and never use the training data. Never use the test data for training, or you will overfit your data. We can use a special operator in Python to implement generator. This is called yield. A generator is actually a loop that keeps reading images or data from the directory. So we can first create an endless loop. Usually creating an endless loop is not a good idea, but it's okay here because we will use the yield operator in Python. The yield function will stop the loop and return one data. Here is an example of a generator that yields integers. Okay, so we first define a generator and we create an endless loop which add 1 each time. And then we use a for loop to read the item from the generator. We use yield to return 1 integer at a time. And then we print the item in the generator. Right? So it will print 1, 2, 3, 4 continuously. And if the item is larger than 4, which is 5, then we can break the generator. This is how to use yield to create a generator. Once we have a generator, we can call the fit generator function of model. So previously we just passed the training data, training tensor to the model. Now we pass the generator. There's one additional parameter that we need to set. We need to set the steps per epoch. We need to define the size of the epoch. And otherwise, is all the same. We need to set the epoch's number. And also we pass the validation generator as validation data and set validation steps. Finally, we can save the model for future reuse. There's one important trick that can increase the accuracy of our model. It's called data augmentation. From computer's perspective, even if there are several pixels different, those two images are different images. So to increase the size of training data, we can make a slight change of original image. Here are several examples. We can make some rotation, cropping, zoom in, and rule out. In this case, we immediately have 6 more training data. Training data size is very important for the accuracy of deep learning models. Keras provides data augmentation in its image data generator. There are a lot of parameters that we can set. For example, we can set the rotation range is between 0 to 180 degrees. Also, we can define the range of width shift and height shift, which can translate pictures vertically or horizontally within a range. We can also do the shear transform, which will randomly apply shear transform to the training data, to the images. And also we can zoom in and rule out the images, flip the images randomly. Also, we can choose the field mode because the different field mode may generate a little bit slightly images. So there are a lot of default functions in the image data generator that we can use to easily augment our data. Although we have learned many algorithms and all the tools are on our hands, it's still very difficult to train a good model. Remember, there are more than 1 million training images in ImageNet dataset. You will need a powerful machine to train an ImageNet model. Moreover, it's not meaningful to reinvent the wheels. So we can use the pre-trained models we can download the models trained by experts in this area and reuse the model. In practice, we will reuse the convolutional part of the model and remove the classifier layers. Remember, we will train the image will go through multiple convolution layers, and then we will flatten the layers, then add some dense layer. The final layer is the softmax. So we will remove the classifier and retrain the new classifier for our task. Okay, because the convolution base has learned how to extract features from the 1 million data in ImageNet. So it has learned a lot of different features. We can reuse the convolution base as a feature extractor and retrain it for new task. This is called transfer learning. And also the convolution-based parameters are usually frozen, because if we change the parameters in the convolution base, it may overfitting because there are so many parameters in the pre-trained model. Keras has prepared many different pre-trained models for us. Almost all the mainstream models are included in Keras, or you can choose to use exception, VGG, ResNet, Inception, or MobileNet, DenseNet, even NASNet. And the number of pre-trained models are increasing. This is very convenient. Let's see how to use pre-trained VGG model. VGG model is most commonly used for extract features because it has a lot of parameters. So first, we need to assign the weights. It assigns the weight trained on different data set. Usually there are two data sets. One is ImageNet, and another one is Places 365. Places is trained using the environment like kitchen, living room, bedroom. So it's for background. ImageNet is for objects. So they are considered complement to each other. So here we assign the ImageNet use the weights of trained on ImageNet. And the second, this is very important. We need to set the include tab to false. We want to remove the tab classifiers and reuse only the convolution base. So to reuse the model, we need to set the include tab to false. Include tab to false. And then we can assign the input shape, or the network is now able to process input of any size. Here we set the size of the images in cats and dogs dataset. We will use the pre-trained VGG16 model to classify cats and dogs images. Now we are ready to add a new classifier on top of the pre-trained model. The pre-trained model is saved in the conv-based model. So we first add the pre-trained model in our sequential model. We add a conv base, and then we flatten the feature map. Now we can add a dense layer between the final output layer. Choose the number you like. And the final layer, because we are doing binary classification, is sigmoid function. We can use summary to see the number of parameters in our sequential model. So the summary will print that indeed we are using the VGG16 model, right? There are 14 million parameters, around 14 million parameters. That's a lot of parameters. It will be very difficult if we want to train a model from scratch. And then we flatten the feature map and use a dense layer to transform the data into the final output sigmoid function. Now the total number of parameters in the model is around 16.8 million. We need to do one important thing before training. As you can see, we have a lot of trainable parameters. In fact, we need to freeze the parameters in the VGG16 model because we want to reuse the weights. To freeze the parameters, simply set a parameter of the convolution base trainable to false. So if you set the model trainable weights to false, then the keras will freeze the parameter for us. If we did not freeze the parameters, it will overfitting because we have around 16.8 million parameters in our model. Sometimes we want to change some parameters of the pre-trained model to get better accuracy. It's called fine-tuning. Usually we will only tune the top layers because the lower layer capture the more fundamental features, and the top layers capture the more semantic features, which we may want to fine-tune for our specific tasks. Here is the architecture of VGG model. Sorry, the button is at the top here. So there are actually 5 blocks in a VGG model. Right? Each block has several convolution layers and 1 max pooling layers. In this case, we will freeze the first 4 block and fine-tune only the 5th block. And finally, we will train a new classifier for the cats and dogs dataset. So here's the code. We can check through the layers in the conv-based layers. I will go through all the layers in the conv-based layers. If the layer name is called block 5 convolution 1, then we set the trainable parameter to true. Otherwise, it false. We set layer trainable to false. So we can freeze parameters layer by layer and fine-tune parameters for specific layers. Let's summarize what we have learned so far. First, convolutional neural networks are the best for computer vision tasks. But in the future, some new architecture called attention and transformer may be better. And the data augmentation is a very powerful way to fight overfitting. Then we learn how to use pre-trained model for feature extraction and retrain the top classifier for our own tasks. We can further improve the pre-trained model on our dataset by fine-tuning the top few layers. Okay. Those techniques are all very important to develop a CNN model for real applications. Deep learning is usually considered as a black box because there are too many parameters, and it's hard to understand what the model has learned. However, for convolutional neural networks, we can actually visualize the filters, especially that ConvNet are developed for processing images. So there are several techniques that can visualize convolution net. The first is to visualize the intermediate outputs of convolution net in the intermediate activations. So we can input an image into the ConvNet and see the activate outputs of each layer. It helps us to understand how successful ConvNet layers transform the inputs and get idea of the meaning of each ConvNet. The second approach is to visualize the output pattern of convolution filters, so we can understand precisely what the visual pattern or concept of each filter learned. Okay, so we can input a grayscale image and see the response, or the maximum response of the filters. The third method is an application, which we can superimpose the filter response with the original image. It can help us to see which parts of an image that was identified as belonging to a given class and the localized object in images. The response is converted into heat maps, and then we can overlap the heat map with original image to identify which part are identified as the target class. Let's see how to visualize the intermediate activations. We want to show the feature maps that are output by various convolution and max pooling layers in a network. Here is an example. Suppose we have this input image, then one of the filters may output this feature map, and we can see that this filter captures the edge and part of the head of the cat. Okay. So let's first read one image. We read cat 1700 as our input image. Then we convert this image into tensor and normalize it. The second step is to import, to read the pre-trained model. Remember, we have trained a cats and dogs model using a simple convolution neural network. Okay, then we concatenate all the outputs of the layers, of all the layers. We loop through all the outputs and concatenate all the outputs together to make a layer outputs tensor. Then we use the Keras model to connect the input, model input, and the activation output. We call this activation model. So now we have the input tensor and the outputs of all the layers in the model. Then we make prediction, pass the image tensor into this model. So after that is ready to be visualized. We first visualize the first activation and plot the first layer activations using a color map. We read this. The original source code can be found in the Francois Choles notebook on GitHub. Here are the activations of first layer of channel 3 and channel 30. The input image, cat 1700, is shown here, and we visualize the output of the channels of first layer. This is the third layer, and we can see that the third layer, the third channel filter has passed most of the edges of the cat. So this filter is used to extract the edges, right? For the channel filter 30, only the pixels around the eyes are extracted, so the filter is used to extract the features of the eyes of the cat. By repeating the previous method, we can visualize every channel in every intermediate activations. First, we want to extract the names of the layers, so we can print layer. So we go through the model layer and append the layer name. Then we select how many images we want to show per row. Okay. For each layer activation and the layer name, we first extract the number of features and save it as n features. Then we get the size of the feature map. The original feature map has the shape that one size and the number of features. So the number of columns is the number of features divided by number images per row. Then we can calculate the size of the display grid. The rest part of the code is to extract the images from the layer activation and deprocess the images, which is remove the mean and divide by standard deviation, because we need to rescale the visual map into the visualized range, into the 0 to 255 pixel range. So we remove the mean and divide by standard deviation and multiply the data with 64 and plus the 128. So this post-process the feature to make it visually presentable. Okay, so now we can save the channel image into the target grid area. And finally we can visualize it. Here is the summary of our cats and dogs small model. As a reminder, we have 4 convolution layers, which is called Conv2D5, 6, 7, and 8. So we can visualize the convolution layer activations. Here are the results. So as for the first convolution layer, we can see that most features are passed through the filters, but some only extract the features of eyes and some extract the edges. Right? And for later, the second layer, the convolution 2D6, there are more filters that has no activation. Means that those filters filter out all the features. They are for different features. For deeper layer Conv2D8, you can see the activations are focused on a larger area because the images are downsized. And we have less activations here. Some filters only activate, has only a few pixels are activated. Some are totally black. There's no activation. We have noticed several things in this experience. First, the first layer acts as a collection of various edge detectors, and most features are passed through the filters. As we go deeper, the activations become increasingly abstract and less visually interpretable. The sparsity of the activations increase with the depth of the layer, and more filters are blank. So basically, the first layer will extract overview of the overall edge of the object, and the later layer will learn specific features and add more detail to the input image. The second approach is to visualize the patterns of ConvNet filters. We can show the visual patterns of each filter is meant to respond to, and we should start with a grayscale input image and then use gradient ascent to maximize the filter response. Here is an example of the filter pattern. Let's visualize the filter pattern in VGG16. So we first import the VGG16 trend using ImageNet and set include top to false. Then we select the block 3 convolution 1 layer. We can use the getLayer function of the model to get the output of the layer. Then we use the mean of the output as the loss to calculate gradient ascent. We select output of first filter. The filter index is 0. Then we call a gradient function of keras gradients to calculate the loss with correspond to the model input. The gradients returns a list of tensors of size 1, and so we only keep the first element, which is one tensor. So we keep first element. Then we normalize the gradient. We add one small value to avoid divide by 0 error. Now we can calculate the loss and the gradient tensor using the Keras function iterate. Iterate takes a NumPy tensor and return a list of two tensors. One is the loss value and the other one is the gradient value. So let's use Keras function iterate and pass the input, model input, and output the loss and the gradient. We can test it by simply pass some zero data and see if it can output the two tensors. Now we are ready to use the iterate function to calculate the stochastic gradient ascent in a loop. We start with a grayscale image with some noise. We set the mean number to 128, so it's a grayscale image, and then add some random noise. Then we define the number of steps that we want to calculate the gradient ascent. Then we call the iterative function to calculate the gradient and the loss value. Then we simply add the gradient value multiplied by the step to our input image. This is how to calculate gradient ascent using Keras. In gradient ascent, we want to maximize the loss. Because the gradient ascent will generate an image that out of the range of normal image, so we need to deprocess the image. Okay. So for an input tensor, we first normalize the tensor, remove the mean and divide by standard deviation. Then make sure the standard deviation is 0.1. So the normalized tensor center on 0 and the standard deviation is 0.1. Then we clip the value between 0 and 1. Then convert the tensor into RGB array. Then return the RGB image. Now we can compile all the previous code together and define a function called generate pattern. It accepts layer name and the filter index as input. Then it will read the layer output from the model, which is VGG in our example. Then calculate the gradient ascent. Calculate gradient ascent here. Use the mean of filter output as loss and create gradient using Keras gradients. Select only first the tensor, then calculate, normalize the gradient, get the iterate function, and then generate a grayscale image with random noise, then calculate the gradient ascent for 40 steps, and finally process the image and return RGB image. So let's try to visualize 4 convolution layers in VGG16. We select the first convolution layer in each of the blocks. There are 4 blocks. And the rest part of the code is just to save the output of the generate pattern and make it as one image. Here are the outputs of block 1 convolution 1 and the block 4 convolution 1. For the output of the block 4, you can see some interesting patterns that looks like the feather of bird or some texture on animal. So indeed, the filter has learned to extract some spatial patterns of the input images. The third trick is to use the final layer activations as heat maps and overlay the heat maps with the original image. This trick can help us to identify which part of the image is responsible for the target class. In other words, which part of the image activate our model and make the model predict the target class. This can help us explain the features learned by the models. This technique is called Grade Cam, published in 2017. So again, let's use the VGG model and apply the Grade Cam on the elephant image. Again, we load the image and convert it into tensors. We need to expand the tensor for additional 1 dimension for a bench input. And then we preprocess the input. It's to generalize color normalization. Then we predict the output. We get the prediction and decode the top predictions. The top 2 predictions are elephant and the tasker. Then we need to find the index of the top prediction. Once we find the index of the predicted class, which is 386, we get the output from the model. It's Africa elephant output. Then we get the last layer, the third convolution layer of the 5th block. And then we create the gradients with the Africa output and the next ConvNet output. Then we use the mean of gradients as our pooled gradients. We call the function iterate function, use the model input and the pool gradient and the last layer activation as output. So then we call iterate to calculate the values. The trick is to multiply the pooled gradient value to the convolution output value and use this as the importance weight of the pixels. And finally, we can generate the heat map of our class activation. So here is the heat map. The heat map says this part of the images activate the output convolution layer, and it's most important. Finally, we can use OpenCV to overlap the heat map with original image. We first read the original image and then resize the heat map using the width and height of the original image. Then we convert the heat map into RGB pixels. Then apply a color map to the heat map to give the heat map color. Then we add the heat map with original image with a 0.4 as the intensity factor. Finally, we will get this image. It shows that the head of the small elephant has caused the largest response of the convolution layers in VGG16. Now let's look at the evolution of CNN. I will review different types of convolutional neural networks in this section. The first convolution neural network was proposed by Jan Lacan back to 1990s. The neural network shown here is LaNet 5, which has 2 convolution layers with subsampling, convolution subsampling, and 2 fully connected layers with 1 output layer. So there are total 5 layers. The later CNN architectures are largely based on this architecture, with different subsampling strategies, activation functions, or neuron connections, training strategies. When talking about CNN evolution, we need to mention ImageNet. ImageNet is a large-scale image database created by Professor Feifei Li. Her photo is here. More than 10 years ago, Feifei has spotted the need of a benchmark for computer vision community. So she decided to create a large-scale image dataset. ImageNet is based on WordNet hierarchy. WordNet has many concepts, word concepts. Each meaningful concept in WordNet described by one or many words or phrases is called a synonymy set or syn set. There are more than 100,000 ConvNets in WordNet, and ImageNet aims to provide on average 10,000 images for each ConvNet. This is a very ambitious goal. So far, ImageNet has around 14 million images for 21,000 ConvNets until May 2021. Fei Li select 10,000 categories from the ImageNet and hold a competition called ImageNet Large Scale Visual Object Recognition Challenge, ILSVRC. The participating teams would evaluate their algorithms on the given dataset and compete to achieve higher accuracy on several visual recognition tasks. For ILSVRC 2017, there are around 700 to 1,300 images for each category, and additional 50,000 validation images and 100,000 test images to evaluate the performance. The total number of images is around 1,150,000. So this is a large competition. ILSVRC have stimulated the advance of technology, especially for deep learning, because deep learning requires a lot of training data. In 2012, the students of Hinton joined the competition and proposed a CNN model. Now it's known as AlexNet. AlexNet won the challenge with large margin and spurred the deep learning boom. Here are the error rates of previous ILSVRC winner. The vertical axis unit is error rate, so the lower is better. The winner of 2010 and 2011 used algorithms based on support vector machine. Is now considered as shallow model, in contrast to deep learning. We can see that AlexNet was around 38% better than previous shallow models. In 2015, the ResNet proposed by Microsoft Asia exceed human level accuracy. During the competition, the researchers find that the more the layers, the deeper the models, the more accurate the model. So the researchers start to push the limit of convolutional neural networks. So the winner of 2014 BGG has 19 layers, and the Google Net has 22 layers. ResNet pushed the limit to 152 layers. Note that the error rate is top 5 classification error, which means your prediction is considered correct if one of your top 5 prediction is the right class. From the ImageNet experience, researchers find that the deeper the network, the more accurate the model. So researchers start to build models and push the limit to around 1,000 layers. But it seems that the accuracy was saturated and did not improve as expected. So now researchers are trying to downsize the model and remove the unnecessary connections and also quantize the parameters. In other words, the recent research is focused on developing smaller model with same accuracy, not chasing the model with deeper layers. AlexNet started the era of deep learning in computer vision. It was developed by Hinton's student Alex, so it's called AlexNet. AlexNet is similar to LaNet 5. It contains 5 convolutional layers and 3 fully connected layers. AlexNet has around 60 million parameters and 650,000 neurons. You may notice there's one major difference between AlexNet and LaNet 5. AlexNet has two branches of convolution net and fully connected layer. But this is not a design consideration. This is mainly because the NVIDIA GPU they used at that time didn't have enough memory to save all the parameters of their convolutional neural networks. So Alex decided to split the model into two NVIDIA GeForce GTX GPU 580, then combine the output of the two ConvNets and make final predictions. Today, our GPU are all large enough so we can use only one branch. AlexNet also include many new techniques. It uses max pooling, relu, and SGD with momentum. In addition, the team proposed a new simple and effective technique called dropout to prevent overfitting. We know deep learning models are easy to overfit. Dropout forces a network to be more generalized by randomly dropping connections between specific layers. So the algorithm can focus on tuning the parameters of the remaining connections. The dropout only happens in training stage. In the testing stage, we also call it inference. In the inference stage, we do not apply the dropout. AlexNet is the first successful CNN model for computer vision. The winner of 2013 ILS-VRC challenge is ZFNet. ZFNet is parameter tuning of AlexNet, so they have many similar operations. ZFNet also uses the convolution layer but with different size of filters and stride. Okay, so it also have 5 layers of convolution layers and 3 fully connected layers. They only use one branch now because the GPU at that time is more powerful than 2012. In 2014, the winner is GoogleNet, proposed by Google, of course. It has achieved a top 5 error rate of 6.67%. That was very close to human level performance. Although the human level test is only tried by one human, which is Andrew Karpathy, Fei Li's previous PhD student, is now Senior Director of AI in Tesla. GoogleNet has proposed many new ideas, including the inception module, which have 4 branches, multiple branches inside one module, and the batch normalization, image distortion, and RMS prop and optimization algorithm. There were 22 layers but reduced the parameter size from the 60 million of ImageNet to only 4 million. So the layers, the network is deeper than AlexNet but has few parameters, which make it easier to train. Let's look at the inception module in detail. There are 4 branches in one inception module, and 3 of the branches go through 1x1 convolutions. The 4th goes through a 3x3 max pooling, then again a 1x1 convolution. You may wonder why we need a 1x1 convolution. But remember that a filter is actually 3-dimensional for an image. So the 1x1 convolution is for the channel dimensions. The 3rd dimension. Remember the dimension of a channel increase with layers, while the width and the height dimension decrease with layers. So if we can apply a 1x1 convolution first and combine or filter out the channel size, reduce the channel dimension, then we can effectively reduce the total number of parameters. That's why inception module has less parameters than the AlexNet. Finally, we will concatenate all the outputs of the 4 branches and make it one vector. Another important CNN network is VGGNet, proposed in 2015. It's a very uniform architecture. VGG is proposed by the Visual Geometry Group, VGG group in Oxford. It's a very large network. It contains many parameters, so it's a preferred choice to extract features, mainly due to the large number of parameters. The author tried different configuration, but the 16 version, 16 weight layers version has achieved the best results. So usually we use the VGG 16 version. We have used VGG to extract features for our cats and dogs dataset in previous example. So from the competition, that researchers find that somehow the deeper model has better accuracy. Deeper neural networks are better than wider neural networks. However, deeper model is difficult to train because of the gradient vanish problem. The information can easily vanish after going through multiple layers. Researchers have found that the deeper networks achieved better performance, but if the architecture becomes too deep, the error rate increases. This is mostly due to the vanish gradient problem, which states that the gradients are too small to change the weights of the deep layers. So the Microsoft researchers proposed the residual network, which is known as ResNet, to solve this problem. ResNet presents using a shortcut, a skip connection. They call it shortcut, to avoid the vanish gradient problem. So this is very effective. The model can choose to bypass multiple layers to use the shortcut directly or use the signal that goes through multiple layers. The residual module simply add the shortcut with the feature map. Okay. So the new model has achieved very low error rate, just 3.57%. That will outperform human performance with 152 layers. However, the error rate of the 34 layer version is close to the 152 version. Researchers have pushed the limit to 1000 layers, but didn't get a significant improvement. Anyway, ResNet is a very effective model, and now almost all models include a shortcut connection in their module. This table summarizes the details of the CNN models we have learned so far. This is made by Vivian Su in MIT. Okay. The first row shows the top 5 error rate of ImageNet. Okay. And this row shows the number of convolution layers in the model. The LaNet has only 2 convolution layers, while AlexNet have 5. VGG have 16, and Google LaNet have 21. ResNet they use 50 layer versions, have 49 layers of convolution layer and only 1 fully connected layers. Vivian Su's research is to build a VLSI chip for running deep learning models. So this table is made from hardware perspective. Let's look at the last 2 rows. The total weights are the parameters that we can train. We can see that VGG16 has the most weights to be trained. And what is MEG? MEG is multiply accumulate operations, which is a basic operation that calculates the multiplication of 2 numbers and save into an accumulator. So we can use MEG to represent the number of operations that we need to calculate to predict a result. Usually the model with larger number of weights requires more operations, so the VGG16 requires the most MEGs to calculate the predictions. Here are some figures that compare the performance of deep CNN models in 2017. The author chose to use the top 1 accuracy here, so this is not top 5 error rate. In fact, top 5 error rate is not suitable for real applications because in practical application, we only look at the top 1 prediction. So top 1 accuracy is better to evaluate the models. Although we have achieved the 3.5 around top 5 error rate using ResNet, the real top 1 accuracy of the best model is around 80, so in 2017. And the figure on the right is very interesting. Okay, it shows the number of operations versus the top 1 accuracy. So here are circles for each model. The larger the circle, the more operations are required by the model. As we can see that the VGG has most operations to make predictions, but the accuracy is around 70. The Inception V4 and the ResNet has much less operations and also less parameters but have higher top 1 accuracy. After ResNet, a new architecture called DenseNet has been proposed. This paper has won the Best Paper Award on CVPR 2017. DenseNet has several convolution blocks, and the idea is to connect the output feature map of the convolution block to all of the later blocks. As we can see from this figure, the output of each convolution block are connected to all the following blocks. So this architecture has a lot of weights and requires a lot of memory to save and process the parameters. But its accuracy is only slightly higher than ResNet. Therefore, this architecture is not popular today. Another promising architecture is exception, which was proposed by the author of our textbook, Francois Cholet. Cholet proposed a depthwise separable convolutions, which assumes that cross-channel correlation and spatial correlation can be mapped, can be processed completely separately. Here are 2 figures from this block which can illustrate the depthwise separable convolution. Suppose we have a 3-channel input, RGB, and then the depthwise convolution will first process the 3 channels independently. And then we will have a 3 independent feature map. Then the depthwise convolution need to be followed by the pointwise convolution, which is focused on apply the filter to the channel dimension. So after the depthwise convolution, there will be a 1 by 1 by 3 filter to combine the 3 feature maps as one. If the output channel, the output dimension is 4, then we will have 4 pointwise filter, which will have different weights to combine the 3 independent input channel. This is stepwise separable convolution. Let's compare the number of parameters in normal convolution with depthwise separable convolution. In a normal filter, suppose we have a 12 by 12 by 3 input feature map, and we want to apply one normal filter, only one. We will select a 5 by 5 filter, and Keras or other framework will automatically match the input channel dimension. So we will have a 5 by 5 by 3 convolution filter, and then apply this filter to this feature map will generate an 8 by 8 by 1 output feature map. Because we didn't use zero padding, and the channel-wise filter will combine the 3 channels into one. So one normal filter will generate an 8 by 8 by 1 output feature map. So what if we want to output a 256 channel dimension? Then we will need to have 256 normal filters. So the total number of weights will be 5 times 5 times 3 times 256, which is equal to 19,200. So the total number of weights is 19,200 weights. On the other hand, the depthwise filter separates the step into depthwise and the pointwise convolution. Right. So first, it separates the channels into 3. It has 3 5 by 5 by 1 filters, and process the input feature map independently for each channel. So we will have a 5 by 5 by 1 multiplied by 3 number of parameters. But in the depthwise stage, it's actually the number of parameters the same as one normal filter. Okay. The key point is in the pointwise convolution. After the depthwise separable convolution, we have a 3 feature map, and now we only need a 1 by 1 by 3 pointwise filter to combine the feature map and generate output. For output dimension 256, we only need 256 number of 1 by 1 by 3 filter. So the total number of parameters for depthwise filter is actually just 547, which is much less than the 90,200 weights of normal filter size. In recent years, researchers find that the traditional convolutional neural networks are over-parameterized and can be reduced. In other words, the traditional model has unnecessary parameters and connections which can be removed. So there's a trend of research embedded neural network, which is develop a model for embedded system. There are 2 major techniques. One is pruning and another one is quantization. Proving is to remove unnecessary connections in neural network and retrain the model. Quantization is to use the less accurate number to save the parameters, to save the weights. We usually use the floating point, which has 32 bits, but it's not necessary. In practice, we can quantize the floating point and use just 8 bits to save our weights. In this case, we can use only 1/4 of the original model size to achieve similar accuracy. The new NVIDIA CUDA can train model using 16-bit floating point, and the Google TPU, the hardware developed by Google for training neural networks model, Tensor Processing Unit, TPU, can also use quantization to use maybe 16 or 8 bits to save weights. So TPU is very fast. Okay, so there are several famous embedded neural network models. One is MobileNet. Here's a figure that shows that MobileNet has much less operations, much less max than AlexNet. However, it has achieved higher accuracy. Right? Although it's still a little bit less accurate than the best model like Inception or VGG, but it's very they are very similar, and the size are much less than the VGG or GoogleNet, than the popular CNN models. As we can see in this figure, MobileNet version 2 has achieved almost same accuracy as the ResNet 101 or 151. In this class, we have covered many modern convolutional neural networks, but there are more new models. So there is a good paper, a survey paper of CNN architectures, which published in 2020. It has more than 70 pages and covers almost all modern CNN models. It categorized the CNN models depends on their features. The first is the spatial exploitation-based CNN models like .NET, AlexNet, VGG, or GoogleNet. The other, like ResNet, are categorized as depth-based CNN. ResNet, Inception v3, v4, or Inception ResNet. There are new models that explore the multi-connection, following the work of ResNet, like DenseNet or Highway Nets. Still, other works explore the width change and width-based multi-connection networks, like Exception is categorized in this area. Another model called the SqueezeNet is also an embedded network that has very small size. Proposed to squeeze the size of channel size, which is like Exception. There are other channel-wise exploitation methods like channel boost CNN. The latest research focus are using the attention-based module, like residual attention neural network, and combine attention with convolutional neural networks. Of course, the latest trend is to use the transformer and does not use convolutional neural network. We will talk about it in later class. I extract a comparison table from the survey paper for your reference. This paper has listed most popular CNN models and summarize their main contribution, also the parameter size and the error rate on ImageNet or Cypher, and the depth of each layer. And the paper has also classified it into different categories based on their features. There are still some important architecture like mobile net didn't contained in this table. Anyway, this paper has given a great overview of current state-of-the-art CNN models. Finally, there is one important line of research that I think it's worth mentioning. It's called a network architecture search. It's part of automated machine learning. The idea is that since we can use the machine to automatically learn the parameters of the filters, why not we also use the machine to find the best network architecture for image recognition or other tasks? So this is the main idea of automated machine learning. The first network for image classification is the NASNet, which is abbreviation of Network Architecture Search. They use NASNet to find a reduced cell. Here's the normal cell, and the NASNet has automatically find a new cell or the new reduction cell. And the NASNet has achieved best accuracy on ImageNet at that time, surpassed all human designed models. Following the work of NASNet, there's a new architecture called Efficient Net in automatically machine learning research area. Efficient Net was published in 2019. The idea is actually simple. Efficient net assumes that there are three main factors that affect the accuracy of CNN model: the width of each layer and the depth of the network, the number of layers, and the input image resolution. So by performing a systematic search for the best combination of the parameters, such as grid search, the efficient net can create a very high accurate model using automatic machine learning. Here are the top 1 accuracy of efficient net and NASNet on ImageNet. As we can see in this figure, NASNet has surpassed the blue line. NASNet has surpassed the accuracy of all human design models, including inception, ResNet, exception, or other combination of ResNet. However, the efficient net can go one step further, or has pushed the accuracy more than NASNet. Although it's not dramatically better than NASNet, but it has achieved best accuracy on ImageNet and achieved the 84% top 1 accuracy. So this shows the effectiveness of the automatic machine learning and the efficient net model. Let's review the important convolutional neural networks architecture that we have learned so far. The first is AlexNet. It's the first large CNN model. It's trained using NVIDIA GPU and includes modern CNN techniques such as relu activation function, max pooling, dropout to prevent overfitting, and optimization algorithm SGD with momentum. The second is the inception network. It proposes the inception module, which apply multiple filters to one input feature map. So it have multiple branches, and then combine the feature map together, concatenate the outputs of multiple filters. Next is the ResNet. ResNet proposes the residual connection, or the shortcut, to avoid the vanished gradient problem. The shortcut can let the feature map bypass the convolution layers, and it successfully trained very deep networks, as deep as thousands of layers. The exception network proposes to use stepwise and pointwise convolution filters to significantly reduce the number of standard convolution filters, reduce the number of weights of the standard convolution filter. We also learned that modern convolution neural network architecture can be learned by the automatic machine learning. So it's possible in the future we don't need to design the CNN architecture anymore.